Hello everyone. Today we are going to analyze this frame using Kani's method. Before analyzing, let us see the frame one time. In this frame, there are two columns, column AB and column DC. Also, there is a beam BC. In the columns, there are no loads. In the beam BC, there is an eccentric point load 18 kN acting at a distance of 2 meter from the point B. The length of the columns is 4 meter. Length of the beam BC is 6 meter. The moment of inertia for the columns is given as 3I. The moment of inertia for the beam is given as 1.5I. This frame is a sway type frame because in the beam BC there is an eccentric point load. Since this point load is not acting in the center, there will be sway. Now let us find the fixed end moments. In the columns AB and DC, there are no loads. So the fixed end moments M of AB, M of BA, M of CD and M of DC will be 0. Now let us find the fixed end moments in the beam BC. In the beam BC, there is an eccentric point load 18 kN. The formulas to find the fixed end moments are minus WAB square upon L square and positive WA square B upon L square. Here W is 18, A is 2, B is 4, L is 6. After applying the values inside the formulas, we are getting M of BC and M of CB. In the Kani's method, we have to find the rotation factor. To find the rotation factor, we have to calculate the stiffness. Let us see the formulas to find the stiffness. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged or with roller support, the formula is 3EI upon L. If the fair end is continuous, the formula is 4EI upon L. In the joint B, first let us find the stiffness for BA. For that, from the joint B, we have to look at the point A. In the point A, there is a fixed support. If the fair end is fixed, the formula for the stiffness is 4EI upon L. Length of BA is 4. Let us apply that. The moment of inertia for BA is 3I. So instead of I, we have to apply 3I. Finally, for the stiffness of BA, we are getting 3EI. Now let us find the stiffness for BC. For that, from the joint B, we have to look at the point C. The point C is continuous. If the fair end is continuous, the formula for the stiffness is 4EI upon L. Length of BC is 6. Let us apply that. The moment of inertia for BC is 1.5I. So instead of I, we have to apply 1.5I. Finally, for the stiffness of BC, we are getting EI. Now, in the joint C, let us find the stiffness for CB. For that, from the joint C, we have to look at the point B. The point B is continuous. If the fair end is continuous, the formula for the stiffness is 4EI upon L. Length of CB is 6. The moment of inertia is 1.5I. Let us apply them. Finally, for the stiffness of CB, we are getting EI. Now let us find the stiffness for CD. For that, from the point C, we have to look at the point D. In the point D, there is a fixed support. If the fair end is fixed, the formula for the stiffness is 4EI upon L. Length of CD is 4. The moment of inertia is 3I. Let us apply them. Finally, for the stiffness of CD, we are getting 3EI. Now let us find sigma K. In the joint B, we have found two stiffness values. We have to add both of them. After adding, we are getting 4EI. In the joint C also, we have found two stiffness values. Let us add them. After adding, we are getting 4EI. Now let us find the rotation factor. The formula is minus 1 upon 2 into K upon sigma K. Using the formula, we can find the rotation factors. We know that this frame is subjected to sway. In this case, we have to find the displacement factors. The displacement factors will be available only in the columns. First, let us enter the story number. In this analysis, we have only one story. In this story, we have the columns BA and CD. For the columns BA and CD, we have already found the stiffness values. Let us enter them. Now let us find sigma K. For that, we have to add these two values. After adding, we are getting 6EI. Now let us find the displacement factor. The formula is minus 3 upon 2 into K upon sigma K. We have calculated sigma K and K values. So using the formula, we can find the displacement factors. In the Kani's method, we have to make boxes like these in the joints. Now let us apply the fixed end moments. The fixed end moments M of AB and M of BA are 0. M of BC is minus 16. M of CB is 8. M of CD and M of DC are 0. In the joints, we have to add the fixed end moments. In the joint B, when we add minus 16 and 0, we will get minus 16. And in the joint C, when we add 8 and 0, we will get 8. Now let us enter the rotation factors. For BA, it is minus 0.375. For BC, it is minus 0.125. For CB, it is minus 0.125. And for CD, it is minus 0.375. Now let us enter the displacement factors. For the column AB, the displacement factor is minus 0.75. For the column DC, the displacement factor is minus 0.75. In the Kani's method, we have to find the rotation contributions. In the joint B, we have two rotation contributions, M-BA and M-BC. And in the joint C also, we have two rotation contributions, M-CB and M-CD. Since in this frame we have sway, we have to find the displacement contributions also. In the column AB, we have the displacement contribution M'-AB, and in the column CD, we have the displacement contribution M'-DC. The formula for the rotation contribution is summation of rotation or displacement contributions at a fair end plus summation of fixed end moments into rotation factor. First, we have to find M'-BA. M'-BA is located in the point B. For the point B, the fair ends are the point A and the point C. In the point A, initially, there will be no displacement contribution, so we can assume that it is 0. In the point C also, initially, there will be no rotation contribution, so we can assume that m dash CB is 0. For the summation of rotation or displacement contributions at parent, we have 0 and 0. The summation of fixed end moments is minus 16. The rotation factor for BA is minus 0.375. Finally, for M dash BA, we are getting 6. For M dash BA and M dash BC, all the values will be same except the rotation factor. The rotation factor for BC is minus 0.125. Finally, for M dash BC, we are getting 2. Let us apply the value of M dash BA here and the value of M dash BC here. Now let us find M dash CB. M dash CB is located in the point C. For the point C, the fair ends are the point B and the point D. In the point B, the rotation contribution is 2. In the point D, initially there will be no displacement contribution, so we can assume that M double dash DC is 0. So for the summation of rotation or displacement contributions at parent, we have 2 and 0. The summation of fixed end moments is 8. The rotation factor for CB is minus 0.125. Finally, for M dash CB, we are getting minus 1.25. We know that in the formula for M dash CB and M dash CD, all the values will be same except the rotation factor. For CD, the rotation factor is minus 0.375. For M dash CD, we are getting minus 3.75. Let us apply the value of M dash CB here and M dash CD here. Now we are going to find the displacement contributions. The formula is summation of rotation contributions at the top and bottom of columns into displacement factor. First, let us find M double dash AB. In this frame, there are two columns, column BA and column CD. In the column AB, the rotation contribution for AB is 0. The rotation contribution for BA is 6. In the column CD, the rotation contribution for CD is minus 3.75. The rotation contribution for DC is 0. So for the summation of rotation contributions at the top and bottom of columns, we have 0, 6, minus 3.75 and 0. We have to add all of them. The displacement factor for AB is minus 0.75. Let us apply that. Finally, for M double dash AB, we are getting minus 1.688. For M double dash AB and M double dash DC, all of the values will be same except the displacement factor. But in this analysis, the displacement factor for DC and AB are same. So we have the advantage. For M double dash AB and M double dash DC, we will get the same value. Let us apply the value of M double dash AB here and M double dash DC here. We have finished the first iteration. Now we are going to start the second iteration. Now let us find M dash BA. Now in the point A, we have the displacement contribution minus 1.688. In the point C, we have the rotation contribution minus 1.25. The summation of the fixed end moment is minus 16. The rotation factor for BA is minus 0.375. Finally, for M-BA, we are getting 7.102. We know that for M-BA and M-BC, all of the values will be same except the rotation factor. The rotation factor for BC is minus 0.125. Let us apply that. Finally, for M-BC, we are getting 2.367. Let us apply the values of M-BA and M-BC. Now let us find M-CB. The latest rotation contribution in the point B is 2.367. The displacement contribution in the point D is minus 1.688. The summation of fixed end moment is 8. The rotation factor for CB is minus 0.125. Finally, for M-CB, we are getting minus 1.085. The rotation factor for CD is minus 0.375. Let us apply that. For M-CD, we are getting minus 3.255. Let us apply the values of M-CB and M-CD. Now let us find M-AB. In the point A, we have the displacement contribution, but the rotation contribution is 0 because in the fixed ends there will be no rotation contribution. In the point B, the rotation contribution is 7.102. In the point C, the rotation contribution is minus 3.255. In the point D, the rotation contribution is 0. Let us add all of them. The displacement contribution is minus 0.75. We know that for M-AB and M-DC, we will have the same value because we have the same displacement factor. For M-AB and M-DC, we are getting minus 2.885. Let us apply them. Now we have finished the second iteration. Let us go for the third iteration. Now let us find M-BA. For that we have to add these three values and then multiply with the rotation factor for BA. When we do that, we are getting 7.489. For BC, the rotation factor is minus 0.125. For M-BC, we are getting 2.496. Let us apply the values of M-BA and M-BC. Now let us find M-CB. For that we have to add these three values and then multiply with the rotation factor at CB. When we do that, we are getting minus 0.951. The rotation factor for CD is minus 0.375. For M-CD, we are getting minus 2.854. Let us apply the values of M-CB and M-CD. Now let us find M-AB and M-DC. For that we have to add these two values and then multiply with the displacement factor. When we do that, we are getting minus 3.476. Let us apply these values. Now let us start the fourth iteration. Let us find M-BA. For that we have to add these three values and then multiply with the rotation factor at BA. When we do that, we are getting 7.66. For BC, the rotation factor is minus 0.125. For M-BC, we are getting 2.553. Let us apply the values of M-BA and M-BC. Now let us find M-CB. For that we have to add these three values and then multiply with the rotation factor for CB. When we do that, we are getting minus 0.884. The rotation factor for CD is minus 0.375. For M-CD, we are getting minus 2.654. Let us apply the values of M-CB and M-CD. Now let us find M-AB and M-DC. For that, we have to add these two values and then multiply with the displacement factor. When we do that, we are getting minus 3.755. Let us apply the values of M-AB and M-DC. In the similar way, we can do more iterations. Here I have done the fifth iteration, here sixth iteration, here seventh iteration, and finally the eighth iteration. I have stopped in the eighth iteration, but you can stop in the fourth or fifth iteration. In the fourth or fifth iteration, you will get approximately equal answers. If you do more iterations, you will get accurate answers. Still, we can stop in the fourth or fifth iteration because we will get approximately equal answers. Now we are going to find the final moments. The formula is fixed end moment plus 2 into rotation contribution at near end plus rotation contribution at far end plus displacement contribution. Let us make one table. In the table, first let us enter all of the members. Then let us enter the fixed end moments. Then let us enter 2 into near end rotation contributions. The near end rotation contributions for AB and DC are 0. For BA, it is 7.802. For BC, it is 2.601. For CB, it is minus 0.828. For CD, it is minus 2.485. Now let us enter the far end rotation contributions. Using the arrows, we can easily enter the far end rotation contributions. Now let us enter the displacement contributions. The displacement contribution is only available in the columns. For AB and BA, the displacement contribution is minus 3.988. For CD and DC, the displacement contribution is minus 3.988. Now let us add these four values, then get the final moments. In this analysis, we have calculated all of the moments. For MAB, we got a positive value. That means it is acting in the clockwise direction. For MBA, we got a positive value. That means it is also acting in the clockwise direction. For MBC, we got a negative value. That means it is acting in the anti-clockwise direction. For MCP, we got a positive value. That means it is acting in the clockwise direction. For MCD, we got a negative value. That means it is acting in the anti-clockwise direction. Finally, for MDC, we got a negative value. That means it is also acting in the anti-clockwise direction. Now let us find the reactions. First, let us take the column AB and find the reactions. By taking moment about B, we can find HA, and then applying the rule sigma H is equal to 0, we can find out HB. Now let us take the span BC and find the reactions. By taking moment about C, we can find out VB. Then applying the rule sigma V is equal to 0, we can find VC. Now let us take the column CD and find the reactions. By taking moment about D, we can find HC. By applying the rule sigma H is equal to 0, we can find out HD. Here you can see the shear force diagram. Here you can see the free movement diagram. Here you can see the end movement diagram. Using the direction of the movements, we have to make this diagram. Here you can see the bending moment diagram. Now we are going to end this session. Thank you for watching this video.